project we started earlier this year. It's a modular stack for zkVMs, or zero-knowledge virtual machines. And I want to start explaining what that actually means. What is a zero-knowledge virtual machine? Or, yeah, more particular, well, what is zero knowledge? And the answer is we're not so interested in that. So you can actually already forget the zero knowledge part again. Instead, we're interested in verifying computations. So the goal is to have a computation that is run on somebody's computer. And as we all know, somebody's computer is not trustworthy. So we want and that somebody computes a result, and we want to check that a certain program run on a certain input computes a certain result. And of course, an easy way to do this is to just run the computation again and see if the result is the same. But then, I mean, what have we gained with that? Nothing. We could have run the computation ourselves to begin with. So, and yeah, there's a very cool result from the 90s that says there's a certain way to encode the execution of a program so that it's enough to read 5 bits in that encoding to verify whether the computation was correct or not. And we're not exactly doing that, but we're kind of making this theoretical result practical. And of course, we're not the only ones who do this. There's a gigantic industry behind that that has developed over the past years, and especially, so this has all started with circuits, and the main feature of a circuit is that it has a fixed length, which means that it can only compute a fixed computation, a computation of a certain size. And over the past months, maybe small number of years, virtual machines have become more and more popular in that area, and the main difference here is that a virtual machine can run a program with a kind of dynamic length. So you can run a program that is quite short or a program that is very large, and this all works in the same framework. And maybe a bit more specific, a VM in this sense is something that has an actual, a fixed program stored somewhere, and then it has dynamic memory and a program counter that points at instructions in the program, you have jumps and so on. So the execution is much more dynamic than in a fixed circuit. Okay, I already said that there was a lot of development on these zero-knowledge virtual machines in the recent time, and if you look at them, then most of them are very specific to a certain execution environment, to a certain virtual machine, to a certain architecture. And most of them also did a kind of an implementation from scratch. So everything is made in a very custom way, built from very small primitives. And this has advantages and disadvantages. So the advantage of building such a thing in a custom way from the ground up is probably performance. So I think this is the reason why people do it. But the disadvantages are, of course, if you want to get an audit for such a machine, then the auditors have to learn every single part, every single custom implementation they did. There's also much more code to read. Then if you, at some point, find out that some architectural decision you made at the very beginning was maybe not the best, then it could be very difficult to change this decision later on. And it generally, it's a lot of work to build such a zero-knowledge virtual machine. And it is often also prover specific. So when I use the term prover, yeah, maybe I'll explain it on the next slide. So, and yeah, the code you build is very hard to reuse because it's specific to your system. Okay, I'll explain prover later on. So, yeah, I would like to make an analogy, and I would like to say that the current zero-knowledge virtual machines, and I actually stand in front of the screen. So currently programs are, so programs for zero-knowledge virtual machines or zero-knowledge virtual machines themselves are written in a very low-level language that is machine-specific. And you can think of this as writing a computer game in the 80s. So you write most of the parts in assembly because it needed to be fast, and you also wrote the computer game for a specific computer in mind, so for a specific architecture. And if you want to port over the game to a new architecture, you essentially have to rewrite the whole thing. And this is of course not how it works nowadays. You use high-level languages that just compile to a different architecture by flipping a switch, and you're also not concerned with low-level routines. So, of course, if you want, you can write stuff using low-level mechanisms, but that will only be the very, very small, highly performance critical sections of your code. Most of the other code is very high level, and it just works. So, yeah, Powdr wants to be something like LLVM for zero-knowledge virtual machines, where you can use high-level languages and swap out frontends and backends as you like. Yes, we also want the system to be very modular, so you can not only swap out frontends and backends, but also some machines you use in the middle to just try out different ways to do things. If there's a new theoretical result in that area, you can directly switch to it and see if it works, if it improves your system. And so Powdr is a programming language, or maybe two programming languages, depending on how you look at it. And this means you write your whole zkVM in this language, and there's a system that understands the language and can analyze it. So you can run optimizations on it. You can check, I don't know, this part, is it actually redundant? Can I remove it? Or can I group some things together? And this is, if you hand write your system, this is not possible. Even if you, I don't know, do things in a modification of Rust, there's no analysis step that would do that for you. And you can also do run an analysis on your system whether it's actually doing what you want it to do. So you can have correctness proofs of your system because it is encoded in a special language. And yeah, the idea is that it's easy to build, easy to test, and easy to audit. So this is an architectural diagram, and here I explain what prover means. Powdr has or supports different front ends, and the list is of course not exhaustive here. We currently support Rust and RISC-V assembly as front ends. C++, if you compile it to RISC-V, it also works. And EVM is something we want to tackle in the future, so direct EVM code as a front end for Powdr. Of course, you can write an EVM interpreter in Rust and have that run on run EVM code, but this is another layer. And Powdr has essentially two stages: the assembly, so Powdr ASM, and the PIL stage, Powdr PIL. PIL is short for Polynomial Identity Language, and this is a language originally defined by the Polygon Hermes team, and we kind of started with the language and extended it to Powdr. What Powdr does is it takes code written in, for example, RISC-V assembly, turns this into Powdr assembly, and then turns the Powdr assembly into Powdr pill, and pill is just a series of equations over polynomials. Essentially, this is what it is. And at every stage, if you want, you can extract the data or also input new data. So you can take Rust and put it through Powdr all the way to the backend prover, but you can also take assembly, so handwritten Powdr assembly, and inject it here. You can also mix and match. You can have Rust code with Powdr assembly, and you can also say, hey, compile this Rust code to pill. I don't want to go all the way to a proof. I just want to have the pill code, and then I want to run some analysis on the pill code, for example. Or you can also take pill code and combine that with Rust and build a system like that. So this is the point where we have a boundary, where we stop. So we do not intend to build a prover ourselves. A prover is, so we stop at the point where we have the polynomial equations and where we have kind of a solution for the computation. So one of the main features of Powdr is that it runs an automatic witness generation. So if you have a program and an input, and you run the program on the input, it generates an execution trace. It generates intermediate values and so on. And this is Powdr will do that for you automatically. And so this is where we stop. We have the trace, we have the values, the intermediate values, and the polynomial equations. And those are then handed over to a prover. We currently support Halo 2, eStark, and Nova in an experimental way. But the idea is that we're totally prover agnostic. So whatever has this kind of form where you have polynomial equations, whenever this is the case, then we would like to support the prover. And the prover does the actual, generates it. Okay. Then now I want to talk a little bit about our RISC-V example frontend. So initially we only built this RISC-V frontend as a proof of concept, a validation that it is actually possible to build such a system with Powdr. So to build a system that compiles Rust code into polynomial equations. But it's working so nicely that we're continuing to improve it and make it faster and more efficient. But the cool thing about this, so even the initial version, unoptimized version, it only needs 300 lines of Powdr code. So you define the whole RISC-V architecture in only 300 lines of this Powdr code. So 300 lines in the Powdr language. And it will automatically do witness generation for you, and it works for any NoSCD Rust code. And as I said in the beginning, we also want to have different frontends, so not just Rust through RISC-V into Powdr, but also Rust through LLVM into Powdr, or directly EVM into Powdr. And the cool thing about that is, so there's for example this Valida architecture, which is a specific LLVM backend that does not have registers. Instead, everything is done with direct memory operations, because in zkVMs memory operations are very cheap. And if you do that, you can actually directly compare compiling Rust via RISC-V through Powdr and compiling Rust via Valida through Powdr, and see which of them is more efficient, or which of them is more efficient in which way. And maybe there's also a way to combine these two systems, or to pick the good parts from one of them and create an even better system with Okay, so here we have an example. We have Rust code on the left-hand side. And as you can see, it uses an external crate. So this is just the unmodified TinyCatcher crate. And it imports some symbols from there, runs a catch-up hash on the input, and then checks that the output is a certain value, so that the hash has a certain value. And so Powdr will compile the whole thing for you and turn this into RISC-V assembly, which looks like that. And this is of course just a very initial part. And then we have a very minimal transform from RISC-V assembly into Powdr assembly. So this is the Powdr assembly language. We won't continue the example here, but I want to talk to you about a little bit more about what you can do with Powdr assembly. And so the interesting thing about Powdr assembly is that it's a language without features. So it's an assembly language that does not have any registers. It does not have any instructions, at least in the beginning. It is so because you can define registers and define instructions, and by that way define your own assembly architecture using the language itself. So the instructions are defined in the language itself, and then they are used in the language. And you can see that here, for example, reg PC defines a PC register, and it has a special annotation that tells us, this is a PC, because it's important for how to go to the next line. So PC has to be incremented to get to the next line. And then we have 4 registers, X, Y, Z, and A. And X, Y, and Z are special. They are assignment registers. I won't get into detail what that actually means. And then we have insert jump. So this defines a jump instruction. And the jump instruction takes a label. And here we have the instruction body. And the instruction body consists of pill constraints. So it has polynomial equations. And what does jump do? It takes a label and sets the PC at the next step to that label. So this means you jump to that label. So program execution jumps to that label. And so this prime here after PC means it's the PC in the next row. So this prime can be used on all the symbols here, and here it means it sets the PC on the next row to L. And we have an assertion instruction here. It asserts that X and Y are equal, and if we write that as an equation, we could, X minus Y equals 0. We can also write X equals Y. And then we have an add instruction, and that one is special because it delegates its operation to an external machine that is imported here. So we have an arithmetics machine, which is defined here and imported into the main machine here. And then we define a function. So you can have, every machine can have different functions, and the functions are defined in terms of a sequence of instructions. It starts with a label start, and then it adds 2 and 1 and assigns that into the register A. And then we assert that A has the value 3. We jump again to the start. So this is a program that is valid. So there's a way to assign values to the variables that do not violate any constraint. So this works. And the arithmetic machine is a different machine in the way that it's not really a virtual machine in the sense that it doesn't have a PC, it doesn't have instructions, but instead it is defined in terms of polynomial equations directly. So you can also do that. So you're kind of reaching from the assembly stage down into the pill. And so while VM machines have functions, these block machines or these constraint machines have operations, but it's kind of similar. And yeah, you don't define registers, but instead you define columns. And here is an equation that just says, yeah, in every row, z needs to equal x plus y. Okay, now going down to the lowest level, the polynomial constraint level. So this is kind of similar to the arithmetic machine we saw before, but instead the difference is that it's self-contained now. And I'm not sure how much I should go into detail here. So this whole system in the end is compiled down into polynomial equations, as I said. And the idea is that you have kind of a very big table with rows and columns. And if you have a equation like this, first times y minus 1 equals 0, this has to be satisfied on every single row in this table. And the system is valid if there's a way to fill the columns such that all equations are satisfied on all rows. And there's essentially, in PIL there's essentially two different types of columns, fixed columns and witness columns. The difference is that fixed columns are defined together with the program and cannot depend on the input. And you can define them like that here. So first is a fixed column, and here the parameter I is the number of the row. So for fixed columns you have direct access to the row index. And it just says if the row index is 0, then the value in that cell is 1, otherwise it's 0. And so you see the first column has a 1 in the first row and then zeros in all other rows. And then we have two witness columns, x and y, which are not defined in terms of a function because they are defined in terms of these polynomial equations. And let's just quickly go through them. So these equations both have to be 0, and on the left hand side there's a product, so they are 0. So the equation is 0 if the left side of the product is 0 or the right side of the product is 0, which means if first is 0, then the right factor is unconstrained because it is already 0, right? So there's no additional constraint on x and y. But if first is 1, so which is only in the first row, then these parts here have to be 0, which means x and y have to be 1. So this is a way to initialize the cell, or initialize these columns, and so the only way to satisfy this is to put 1s in the first row here. And then the lower part here, let's ignore this left thing. The lower part says x prime minus y equals 0, which essentially means x on the next row is equal to y. So x on the next row is equal to y on the current row. And this just copies over y's from the row before to x in the next row. And then the last part here, that is actually the Fibonacci series definition, that y on the next row equals x plus y on the current row. And that's how you fill up so that determines the rest of the cells in this table. Okay, I wanted to make a quick demo. So this is essentially the example we saw on the slide. And now when I run Powdr on that, so I just do cargo run minus R is we want to run it in release mode because it's fast. Rust means, or actually, yeah, I can just run it like that. And then we see the options. So this, yeah, it's just the different ways you start with it. You can start with PIL, you can start with Rust, you can start with RISC-V assembly, and so on. And we want to start with Rust. And so this is the directory that contains a Rust crate. So it just compiles the Rust crate. and we outputted that directory, and I ran it before, so this directory is not empty, which means we need to force override. And let's see if that works. Yeah, so it compiles this stuff into RISC-V assembly, the Powdr assembly, the pill, optimizes the pill, and now we have the main part where it deduces the weaknesses, so where it runs the actual program. And so it says it detected a loop. This means that so at the end of the execution, we just have an infinite loop that just goes back and forth between two instructions, and we detect that and can speed up the witness generation here. Yes, so it is done. It wrote a binary file containing all the values for the fixed columns, and it also wrote a binary file containing all the values for the witness columns. Now let's see what did it actually generate. So we can maybe start with, so this is the RISC-V assembly file of the catch-up. Yes, this should be the main. It's a lot of code because it's almost the whole crate. And we run some analysis on that and actually remove uneven code. Yeah, I can't find the main function now, but it won't be too useful anyway. So you see, it's a lot of assembly files, also a lot of data. So these are lookup tables here, and we also have to import some stuff that is part of the Rust compiler or Rust runtime, and then this is the Powdr assembly file that is generated. So you see here the registers, the PC, then some assignment registers, and then the 12, so the 32 registers of the RISC-V architecture. So this is actually quite bad for zkVMs. Because, as I said, memory access is cheap, so we wouldn't need that many registers. And then here's the definition of the architecture. So what are the instructions? We have jump, load label, branches, comparisons, binary operations, some assertions, division. Yeah, you can actually see here 275 lines. So below here, the actual program starts with the instructions. So the definition of the architecture is 275 lines only. Okay, I cheated a bit because we have some external machines, so for arithmetic and binary operations, but they are not too large either. So maybe, I don't know, 20, 30 lines each. And then there's the debug information here. And here we have the Powdr assembly code. And then this gets compiled down to pill code. You can see here. And you might recognize a lot of this because, yeah, the instruction definitions, they have pill code in their bodies, and this gets directly translated. But what is very different is the actual program, so the sequence of instructions in the program that doesn't exist anymore. That instead gets translated into a gigantic table, or a set of tables here, which is actually, yeah. So this is lots of zeros and ones, and we have one column per instruction, and it has zeros and ones saying whether or not the instruction is used for that line. And we run an optimizer on that. Get this code here, and yeah, functional binary code. yeah, this is the demo, I would say. Unless you want to see something else.
The output, like the commits and constants, those are things that you would take and give to the prover. Is that correct?
Yes, yes. There's actually I mean, you can also there's options to also directly run the prover from here, but I don't want to do that here now.
So okay, I don't know that much about the technology behind this, but outside of this demo, is there anything that people already use about Powdr or have built with Powdr, or is this like really just what you just showed us and now people are starting to use it? How can I conceive of use cases for this?
So maybe this was kind of implicit, but I mean the prime use case for this is of course verifying blockchains. So you just encode the whole history of a blockchain into a single computation, a single proof, and you verify it, and you're synced, right? So you don't need to verify anything. Or also verifying one blockchain in another. So layer 2 blockchains verified in a layer 1 blockchain. But you were probably asking about specific applications of Powdr, right? So we are currently exploring partnerships. So we don't have. So I mean, this is of course not a production, right? This is just in the research stage now, in the prototype stage. Yeah, and we're exploring partnerships.
Okay, interesting. Thanks.
How big is the witness actually? So you have this one particular execution of that you showed. Like, how big is the witness for that one, for example?
I mean, you mean the witness file here?
Yeah.
Yeah, 500 megabytes.
Wow.
But this is that's the proof will be much smaller, right? So this is just what we give to the prover, and then it will create a proof out of it.
Right.
And the cool thing is that in some proof systems you can get a proof that totals like 4 curve points. Yeah, so you can have 4 curve points that is entire proof. Right, for any
Yeah,
amount of
if
data.
you turn it into Snark, then there's a way to do it.
Like less than a kilobyte, basically, right?
It's less than 100 bytes. No, less than that.
Depends on the curve, I would say.
Yeah. I mean for BN.
Right.
Each one is 256 bits. So 8 times 32 bytes.
Less than a kilobyte. A few hundred bytes.
And yeah, the cool thing about this technology is that, so the input is of course also part of the proof. And the input here is not the program, it's just the input to the program. But of course you can always hash the input. Just have the hash be the actual input and then verify, oh yeah, I know some input so that this program runs this and that.
More of a general question again. What's your motivation for working on this? Is this for making blockchains faster, more scalable, more decentralized? I mean, maybe all of the above. But what's the what inroads are you trying to make into what problem space?
I mean, in
If that's
the
not too
blockchain space, the motivation is of course to be able to scale blockchains, right? To be able to move stuff into layer 2 and be able to verify things faster. So it actually reduces the need for decentralization, right? Because you need fewer people to actually check stuff. But I don't know, yeah. But I mean, and the more general motivation is just, I don't know, I really find this technology to be very exciting, and I want to be easier to use that technology and bring it into mainstream, because I don't like trusting other people to execute stuff correctly. I want to verify it. I want to verify quickly. That's what I find exciting. And I mean, I don't know. Of course, blockchain is the main use case here because of the interest and the kind of trust assumptions. But I could totally see having a computation that does hydrodynamic simulation and then verifies that a aerodynamic simulation and verifies that a airplane doesn't break down, and then condense it into a proof, and then you can verify, oh yeah, they ran the simulation correctly and the aircraft works. Or how do you say in English? Yeah, do some analysis on a building that it doesn't run down and store it in a zk proof.
Alrighty then, thank you very much, Christian.
Thank you.